All right, in this video we are going to talk about the graph of the secant function. So in order to graph the secant function, what I recommend doing is using the cosine function as a guide. You tend to graph cosine and sine more than you do secant and cosecant, and so just to me, as you're working through your courses in math, just seem to be more familiar with sine and cosine. And if you remember what sine and cosine look like, then it's really not that difficult to figure out what the graph of secant will look like. So what I've done over here in Desmos is I've graphed out a bunch of points on the cosine function, and we can even graph that cosine function if we want to, but I'm going to change it to dashed line because it's not the graph of it's not going to be on the graph of the secant, but we're just kind of using the cosine function as a guide for the secant, and that's because of that relationship that we have between the cosine and the secant, that the secant is 1 over the cosine, or 1 over the secant is cosine, however you want to look at it. So starting with this point right here, we have the point 0, 1. Okay, so the x value will be 0, and then here on the graph of cosine, this would be the cosine of 0, right? That's the way that works, which is 1. So on the secant, it would be 1 over 1, which is just 1. So I'm just going to put 1. So that point 0, 1 is actually on both the secant, cosine, and the secant. All right, so the next point here is pi over 6 and square root 3 over 2. All right, so pi over 6 would be this next point. If we look at what it looks like on the secant, 1 over square root 3 over 2, like so, which is actually, if you do the math on that, which I'm not going to go through because it would, if I do that for all the points, it would take a while. But it's 2 square roots 3 over 3 if we flip that over. Okay, and next point would be here, pi over 4. And that point would be 1 over square root 2 over 2, right? If the value of the cosine is square root 2 over 2, then for the secant it would be 1 over that. If you work out the math on that one, it comes out to be square root 2 there. So that's where that would point be. So you can see cosine's kind of going down, and then the secant is going up. All right, next would be pi over 6. Or sorry, pi over 3, right? And the value of cosine on that one is 1/2. So we'd have 1 over 1/2. And so that would wind up to be a 2 right there if you flip that over. All right, next one is pi over 3, or pi over 2 rather. And so at pi over 2, the value of the cosine is 0, so the value of the secant would be 1 over 0, which is undefined. Okay, so and so what will end up happening here is that for the secant, it will have a vertical asymptote at pi over 2. So again, I'm going to draw that as a dashed line, and that's going to be true, right, at every place where the cosine is 0. So every place where the cosine crosses the x-axis, that will mean the secant will be undefined, and the secant will have a vertical asymptote at that point. All right, so we can keep moving forward here. So the next point on the unit circle would be 2 pi over 3. At 2 pi over 3, it's going to be 2 as well, right? So you have negative 1/2, and so it's going to if I flip that over, it's going to come out to be a -2 there. The next place on the unit circle would be 3 pi over 4. Right? At pi over 4, I had square root 2, but this one's going to come out, since these points on the cosine are down there, they're going to be below the x-axis, and so they would be negative, so that would be minus square root 2. The next one would be at 5 pi over 6. That's this point right here. And that's going to be negative square root 3 over 2 on the cosine. So on the secant, it's going to be minus 2 square root 3 over 3. Like so. The next value at pi, the value of cosine of pi is -1. So 1 over -1 is -1. And so you're going to have it here. Okay. All right. And so we can keep following this process and graphing these points out. And so I'm going to just take a little shortcut here to do that. But you could see how that goes. I think I have all those done. All right, so and let's color all of those points purple, so they're all the same color. All right, I'm going to turn this off a little bit. All right, so you can kind of see what's going on here. That the secant, right, is going to be above and below the cosine. Everywhere where the cosine is 0, right, you're going to have a vertical asymptote. So right here at 3 pi over 2, we're going to have another vertical asymptote for secant. Okay, and so that's what it looks like. So, all right, if I'm going to graph cosine back, and then if we graph the secant function itself, you're going to see it's going to go through those purple points like so. All right, and so you can see that the secant function, right, is tied in pretty closely with the cosine function itself. Okay. So everywhere there's a high point or low point on cosine, you're going to have a branch, right, of the secant function, a piece, a kind of a U-shaped piece, even though it's not exactly like a U. So on the high points, that U-shaped piece is going to go up. On the low points, that U-shaped piece is going to go down. Everywhere where the cosine crosses through the x-axis, then you're going to get a vertical asymptote of secant. All right, so now I'm going to turn everything off here except for the secant function itself. And these two asymptotes, okay? All right, and so that's what the graph of the secant function looks like. So if you know what the cosine function looks like, the basic cosine, you can get the basic secant pretty easily just by drawing it out. So generally that's what, a lot these days you don't have to do a lot of drawing by hand of these graphs because of technology, and that's a good thing. But it also is helpful to know the connection between the cosine and the secant in terms of the graph. All right, so that's what it looks like. All right, let's take a look at the properties of the secant function. So first off, the domain of the secant function is all real numbers x, where x is not equal to 2k plus 1 over 2 times pi. So if you haven't watched the videos where I explain what this notation is, the videos for tangent and cotangent, is where I first explain those. then you need to go back and watch that and make sure that you understand this notation. But again, basically it's a list, right? And this is a convenient and short way to write an infinite list of numbers. And in this case of the secant, that infinite list of numbers are all the odd multiples of pi over 2. So 1 times pi over 2, 3 times pi over 2, 5 times pi over 2, 7 pi over 2, negative 1 times pi over 2, negative 3 times pi over 2, and so on and so forth. So those will all be places where the secant function is undefined. If I try to take the secant of pi over 2, I'm going to get undefined, or if you're on your calculator, you'll get an error. Or if I try to take the secant of minus 3 pi over 2, again, you're going to get an error. Those are not numbers where it's defined. And they happen to be the same places where the cosine, right, function is equal to 0. So wherever the cosine function crosses the x-axis, that's at the odd multiples of pi over 2, then that's where you're going to have a place that's a number that's not in the domain of the secant function. All right, the range of the secant function is negative infinity to negative 1, union from 1 to infinity. So in other words, remember the range is the set of all outputs for inputs that are in the domain. So the domain is basically the numbers that you're allowed to plug in, right? The range is the outputs for those numbers. And so what this says, this is just a fancy way of saying that the numbers that you get as outputs for the secant function are negative 1 or less, or 1 or bigger. You can't get anything in between minus 1 and 1. And you can see that, right, because there is no graph in between 1 on the x-axis and minus 1 here. There's nothing in this little strip between those two places, right? So y equals 1 and y equals minus 1, if you look at those two horizontal lines, there is no graph in between these two lines. The graph is all either above or below those. Okay, so if I look at some of the outputs that I can get for the secant, you're going to see that they're all 1 or bigger, or negative 1 or lower. Okay, so that is the range of the secant function. The period of the secant function is 2 pi. You can see it repeats exactly like the cosine does. So it's really no mystery as to how that works. Just like the cosine function, right? The first period that we graphed it over, and the first time that we graphed it was 0 to 2 pi. You can see since it's tied so closely to the cosine, it's going to have exactly the same period as the cosine function. In other words, it takes it 2 pi units to repeat the graph. So if you start at 0 right here, it goes up, and then it has this part that goes down, right? And then it has this part that goes down, and then at 2 pi, notice it's starting doing the same thing it was at 0. It's above the x-axis going up. Right, so here it's above the x-axis going up, so that means it started repeating from right here. So the period is 0 to 2 pi on this one. And likewise, the vertical asymptotes are exactly the same place where the points that are not in the domain of every place where the cosine crosses the x-axis, you're going to have a vertical asymptote. And this is the typo here, this should actually be equals, not, this one should be not equals, this one should be equals, right? Because the equation of the vertical asymptotes, the form is x equals the number, right? So x equals pi over 2, x equals 3 pi over 2. All right, so that's what the cosine, or rather secant function looks like here. All right, in the next video, we're going to talk about the cosecant function. It is very, very similar to the situation for the secant. Instead of being connected with the cosine, it is connected with the sine function.